All right, so far in this unit, we have learned about hypothesis testing, and we focused on two types of testing. We had our t-test and our one proportion or our proportion z-test. Both of these came if we had like two samples or two proportions that we could compare to each other, but generally we've been working on our t-test and our proportion z-test. There is another type of hypothesis testing that we want to be aware of and be able to run, which is our chi-squared test. There are three different kinds of chi-squared test. There's a goodness of fit test, a test of independence, and a test of homogeneity. We will go over all three of those today. Two of them use the same function in your calculator. They run almost identical. And then the goodness of fit has a little bit of a different process, but very similar to what we've been doing so far, just a different type of test for different data. So I'm going to go over a little bit of notes for each of them, and then I'm going to talk about, I'm going to go over an example as well. So the first type is our goodness of fit test. So goodness of fit test is used to test the hypothesis that an observed frequency fits or conforms to some claimed distribution. So a goodness of fit test is the data that we got a good fit for the distribution, for the entire population's distribution. So for a chi-squared test, all three of these actually follow the same conditions, and there's only two of them. One, that the data comes from a simple random sample, which we've done before. And then two, that all the expected values are greater than 5, greater than or equal to 5. And as we do examples, I think that will make more sense. So here's the formula if we wanted to find our own goodness of fit test. We are very fortunate that our calculator does it for us, so we don't need to be able to, but there is a formula that we could use. One of the things that we need to know is how to find degrees of freedom. Degrees of freedom is just the number of categories minus 1. And I'll show you how that comes into play with some of the practice problems that we're going to end up doing. So for number 1, or for our goodness of fit test, there are a couple of letters that we end up using in our formula. O is our observed frequency. E is our expected frequency. So what we're trying to find is, does our observed frequency have the same distribution as our expected frequency? And then K represents the number of different categories, and N represents the total number of trials. The same thing is true for all of these hypothesis tests. If you have a small p-value, so if your p-value is low, you reject the null hypothesis. If your p-value is not lower than your significance level, then you failed to reject. So I think it makes more sense to look at this in context of a goodness of fit problem and how we'll end up running the test. So right now we're on page, 173. I'm going to have you flip to 174 to actually look at a goodness of fit problem. So if you flip to 174, a little bit under our notes, I put all the notes for the three of them in one spot and then the examples after them. So if you want to go ahead and look at 174, we'll look at this example of goodness of fit. So it says Jolly Ranchers competitors believe that Jolly Ranchers purposely put more green and purple Jolly Ranchers in each bag, knowing that these are the worst two flavors. We collect a random sample of 10 bags, each bag having 100 pieces and 5 flavors. Our hypothesis is that the proportion of the 5 flavors in each bag are in fact the same. So our hypothesis, we're testing the claim that the proportion of the 5 flavors are in fact the same. So we have some data here. We observed these values, and we want to see if they match up to the expected values that we're claiming. So if we think about this, these are our observed values. If we think about what the expected values would be, if we think in 10 bags, they all have the exact same amount of each color, that would mean in 10 bags of 100 pieces, We have 1,000 pieces of candy that we're considering. So of those 1,000 pieces, right, if I divide 1,000 divided by 5, I get that each of these should have 200 pieces. Right, we're expecting that there is 200 of every color if each of those is going to be exactly the same. Okay, so what our test is gonna do is compare our observed values with our expected values and see if they're really a good fit for each other. Before we do that, we always wanna check our conditions. In this case, our simple random sample, yes. All right, we collected random samples of 10 bags. And then are our expected values greater than or equal to 5? Well, in this case, all of our expected values are 200. So since those are all greater than 5, we are good to keep going. This is going to be a goodness of fit test. And we are testing the claim that the proportion of the 5 flavors now, for all goodness of fit tests, our null and alternative hypothesis are actually the same. They don't have any numerical pieces to them. The null hypothesis is that the sample we have, or the observed values, fit the distribution, which is our expected values. And our null hypothesis, our alternative hypothesis is that the sample does not fit the distribution. So those will always be the same null and alternative hypothesis for goodness of fit. In this case, our claim is that they're the same. So our claim is that the distribution will fit, that this does match this pretty closely, or within reason. All right, so if we turn our paper over, we will run our test, our goodness of fit test. Remember I talked about that degrees of freedom is n-1 or k-1, and this is just the number of categories. So since I have 5 flavors, 5 minus 1 would give me degrees of freedom of 4. Okay, so to run our goodness of fit test, the first thing we're going to have to do is make a list. Make our list in L1 and L2. We put our observed values in L1 and our expected values in L2. So when I go to my calculator, I need to put that stuff on that was on the table of the previous page. I need to put this stuff onto a list. So I'm going to hit Stat, Edit, and then I need to put these values into list 1 and list 2. So I'm going to clear my list first. So my observed values go into list 1. And my expected values, which are all the same in this case, go into list 2. Great. So the first thing I have to do is I have to type these into my list before I run my test. So then I'm going to do my stat, go over to test, and I'm going to find, if I scroll down, my chi-squared, but then I want the GOF one. That's goodness of fit. So that's the letter D, chi-squared GOF test. That's the test that I'm going to run for this. So then it asks, are your observed values in list 1 and your expected values in list 2? Yes, they are. My degrees of freedom in this case are 4. And then I'm going to hit calculate. So what I get from here is my test statistic chi-squared is 52.75. My p-value is 9.61 e to the negative 11. So that means there are 10 zeros, right? This e to the negative 11 is scientific notation, meaning I'm moving this 11 times to the left. So there will be 10 zeros before my values. So that is a significantly low p-value. Now we were running it up against, did it tell us? I don't think it told us. So we'll just use 0.05. Doesn't really matter with the p-value that low. We're going to reject that null hypothesis. So if we go back here to what our null hypothesis was, we are rejecting this, meaning we're rejecting our claim that the proportion of the 5 bags are in fact the same. Yeah, we don't have enough evidence to support that. So we can write there is sufficient evidence to reject the claim that, and then we just copy exactly what we wrote as our claim. The proportion of the 5 flavors in each bag is the same. Yeah, we found that our observed values do not match, do not fit the distribution of our expected values. So we're rejecting that claim. All right, so that is our first type of test, is our goodness of fit test. So we're going to go back and go ahead and go back to page 173 and talk about our second type of test. Our second type of test is our test of independence. All right, so for our test of independence, we're testing that our rows and our columns are independent of each other. So just like our goodness of fit had the same null and alternative hypothesis, and if we wanted to write them somewhere, right, I wrote these two down here. So maybe that's helpful to have, so that you always have your matches. I should have written fit. Your sample fits the distribution and does not fit. Goodness of fit would make more sense in this case. But just so you have as a reference, anytime you're doing a goodness of fit problem, this is your null and alternative hypothesis. Just like anytime you're doing a test of independence problem, this is your null and alternative hypothesis. So independence is talking about the relationship between the two variables. So anytime you're doing a test for independence problem, you're looking at two variables and you're considering, are they related or not? So we'll look at a problem together and we can kind of see the process for our test of independence is different than what we've seen before, but it's still pretty simple and straightforward. So let's look at an example of test of independence. So we're going to need to go to page 175 and we want to test, right? Here's our example. AMC stated for them to make more money, they need to show more children's movies because children's movies bring in more snacks than any other genre of movie. The table below provides a list of movie genres and whether or not the patrons of those genres bought snacks at the theater. Our claim is that the type of movie and whether or not people bought snacks are independent. Yeah, so a lot of the times the problem is going to tell you that it wants to know if they're independent or not, or related or not. So it kind of gives you a hint that you're doing tests for independence. The owner of the movie theater wants to estimate how many snacks to buy. We randomly collect data for 600 people at our theater. For each person, we know what type of movie they saw and whether or not they brought snacks. So we are testing, is the type of movie independent of if they bought snacks or not? So those are the two things that we're comparing to each other. So remember, we already discussed that your null and alternative are decided for you because you're doing a test of independence. Our null is that the two are independent. The alternative is that they're dependent. So you can either put the rows and columns are independent, or you can say you can put it in the context of the problem. It doesn't matter to me. The genre of movies and snacks purchased are independent. The genre of movie, or the movie genre, I guess is a better way to write that, and snacks purchased are dependent or not independent. Either one is fine. We are claiming that they are independent. So we are claiming the type of movie and whether or not you bought snacks are independent. So we are going with the claim being our null hypothesis. So we can go back, sorry, I've been kind of skipping around, but we can go back and check our two conditions. Our first condition is it's a simple random sample. We did say we randomly collected data. And then our other one is that our expected value is greater than or equal to 5. In this case, we're going to assume that's true because all of these values are greater than 5. Once we actually run the test, I will show you how to find the expected values, and we'll make sure that they are greater than 5. So then our degrees of freedom, remember the number of categories minus 1. So 4 categories minus 1 would give me 3. So now I need to run my test. In this case, it's a little bit different. We're actually going to make a matrix. So the first step is we're going to make a matrix. To do that, we are going to hit second, and then this X minus 1 button, you see how it has matrix written above it? So second, and then this button is our matrix button. So second matrix. And then we're going to go move over until we get to edit, because we need to edit our matrix. So now we want our table to be something that we can type in. We're going to basically match that table in a matrix form. So as you can see, my matrix is actually the right size. I have 4 columns and 2 rows, or 2 columns and 4 rows, I apologize. And so we just want our numbers to fit within this matrix. So a 4 by 2 is the right size for us. And now I'm just going to type these values in. So I have 50 and 75, 125 and 175, 90 and 30 and 45 and 10. So once we type into our matrix, we're good to go and run our test. We only have to type into matrix A. The nice part is when we run this test, it actually puts the expected values into matrix B for us after we run the test. So we're going to hit stat, go over to test, and then this is our basic chi-squared test. We're going to pick letter C, which is our chi-squared test. So it asks, are your observed values in matrix A? Yes, we did that. And then it's going to put the expected values into matrix B. So we can go ahead and hit calculate. And it has those values for us. So chi-squared is 65.01. And we'll go over to the next page. Our critical value, if we're testing against a significance of, let's just say 0.05, our p-value is 4.99 e to the negative 14. That means there's 13 zeros before this number, so it's a very, very small number. So we're going to go ahead and reject the null hypothesis, which means we are also rejecting the claim that these are independent. Yeah, our claim was that they were independent, and we're rejecting that. Okay, so we actually proved that they are not independent in this case. Okay, so now the last thing I wanted to show you is how you can go back and see those expected values. We don't really need them except for to check our conditions, but it's good to know where they are. So if we go back to our matrix, second matrix, remember I told you that when you ran the test, it put all the expected values into matrix B. So if we actually select matrix B and hit enter, all of those expected values are going to show up for us. So what they really expected this value to be was 64.58. This was supposed to be 155. This 62, 28.42, 60.42, 145, 58, 26.58. So these are the values that they expect to get in this given situation. Given the values that you've gotten, this is what they would expect on a normal for an entire population. Okay. So that is our test of independence. So we just have one more type of test left. So we're going to flip back to 174. Right, I did this on purpose so that kind of all your notes were in one place. On 173 and 174, it goes over goodness of fit, test of independence, and then on the back, test of homogeneity. And then after that is the example of all three of those. So for our test of homogeneity, we are testing if different populations have the same proportions or the same characteristics. So for test of independence, we were testing two things against each other. Test of homogeneity, we are testing multiple things against each other. So we're testing if they all have the same outcome that you would expect. So just like I said before, they all have the same null and alternative hypothesis. So if we want to do this, our null is that all populations fit the same distribution. All populations do not fit the same distribution. So again, this is always going to be your null and alternative hypothesis for your test of homogeneity. We're testing if different populations will come out to have the same distribution or if all the populations have different ones. And again, I think once we see an example, it makes a little bit more sense of what we're asking. So if we go ahead and we're going to go back to page 176 now and do our example of our homogeneity. So this says Hallmark is thinking about adding more Christmas movies to the lineup, but wants to figure out the age of their target audience. They believe that women over 50 are watching more than women under 50, so they want to change their movies to reflect that. With that being said, a study was conducted asking 300 randomly selected women if they watch Hallmark movies and which age category they fell under. The results are listed in the table below. So we are testing that different ages have the same distribution, the same number of people are watching it regardless of age. It is very similar to test of independence because test of independence is looking at are the two independent, but this one could have multiple, right? Test of independence is really going to look at two categories. We could look at multiple categories for our test of homogeneity. We're looking at at any age category, we're looking at do they have the same distribution of yeses and nos? While test of independence is asking if the two are independent or dependent of each other. So our prediction, our null hypothesis is that they have the same distribution. So the same number of people in age 50 that are yeses is the same for the people over 50. The same amount of no's is the same amount of no's. So the two populations, in this case, there's just two populations. The two populations have the same distribution. And the two populations have different distributions or do not fit the same distribution. And we're actually looking at a claim that women over 50 are watching more than women under 50. So really in our test of homogeneity, we're comparing these two to each other, while in our test of independence, we're testing this category to this column to this row. So just like all the other ones, our conditions are the same. Is this a simple random sample? And then are all of our expected values greater than 5? Again, we're going to assume this is true, but we'll actually test that theory. We'll go back and check at the end if that's true or not. All right, so to run our test, our degrees of freedom, we only have two categories. So 2 minus 1 tells me that my degree of freedom is 1. This runs just like our test for independence. So we're going to do our matrix first. We've got to type our value into our matrix. So just a refresher on how to do that. We hit second matrix. We're going to go over to edit. And then I remember I'm only going to type in these values. So I need this size to match this size. So my matrix is a 2 by 2 in this case. And then I'm going to type in my numbers so that my tables match from my calculator to my paper. All right, so after we type in our matrix, then we do our stats, test, and then we're going to pick that same chi-squared test that we picked for our test of independence. So stat, test, C chi-squared. Again, are my observed values in A, or my expected values will show up in B, and I will hit calculate. So in this case, my chi-squared value is 1.29. My p-value is 0.31. And if I test that against really any critical value, this is much bigger than this, so I'm going to end up failing to reject my null hypothesis. So our claim was that women over 50 are watching more so that they don't have the same distribution, but we are actually going to keep our null hypothesis, meaning that they do have the same distribution. So there's not enough evidence to support our claim that women over 50 are watching more than women under 50. All right, so those are our new 3 types of tests. I think the best way to kind of get good at these tests is just to practice them. I think that a lot of our steps in writing out our test are similar to ones that we've seen before, but the process is looking a little different this time. So there is some practice pages for you to do practicing these 3 types of tests. So once you're done with the video, you can go ahead and move on to the practice.